So it's my pleasure to introduce our next speaker, Dr. Tony Lupo, and he is a familiar face to all of us here on campus and in the state, in the region, and even nationally. So Tony is a professor in the School of Natural Resources and also the chair of our Department of Soil, Environmental, and Atmospheric Sciences. And this morning, Tony is going to talk about the science of drought and flood prediction. Tony.
Well, thank you for the introduction, Shibu. And today we'll talk about drought and flood prediction, but I'm going to focus on drought since that was what we experienced in the last year. But really, drought and flood prediction are two sides of the same coin in the way that we do things, because what we're looking at is, as Chris was saying, the position of the jet stream. Much of what Chris was talking about, we find in our results as well, and we use some of the things that he said to make our forecasts. Weather forecasting, of course, is a dynamical problem. And weather forecasting can be done pretty well with a dynamic model from about 10 to 14 days. Once you get beyond that, and once you get into seasonal prediction and annual forecasts and things like that, you really need to use other approaches, statistically based approaches. And when we do long-range forecasting, we use things like contingency or persistence and trends and analogs. And all of those things have a statistic basis. Dynamical modeling can be used as well, as Chris was showing. But what dynamical models produce, of course, will be an ensemble of statistics in the end. So this is what we're going to take a look at today. But I wanted to begin with a no-brainer, at least, that the summer of 2012 in Missouri was very hot and very dry. Well, how hot was it? If you look at the statistics for Missouri, the mean summer temperature here for only the 6th time got above 80 degrees. Hot summers like last year are very infrequent and are way off the charts. If you look at the statistical distribution for temperatures in the summertime, that distribution is fairly narrow. So when events like this come along, they tend to be way off the scale. And to show you what I mean, 80.3 ranked as number 6. Number 7, the average summertime temperature was 79 degrees, so way below what these 6 summers were. All right, so this was a truly remarkable summer in that context. With precipitation, it was dry, and we ranked it the 10th driest summer, thanks to a reprieve from Hurricane Isaac. Hurricane Isaac came into our region at the last minute and dumped about anywhere from 3 to 7 inches across the state. And so we only ranked as the 10th driest. And when I talk about the summer season, I'm talking about June 1st to August 31st. I'm using the meteorological definition of what summer is. All right, so June 1st to August 31st. How last second was Isaac? Well, here you go. This is hard to see, but the rain began in earnest just before 8 in the morning on August 31st. So it was really last minute. And this is the kind of thing you deal with statistics, especially when you appoint arbitrary start and stop dates for summer. But even with that rain that gave us a reprieve, you can't look at temperature and precipitation processes as two different entities. You really have to combine them and look at them in a combined sense. So when you do that and combine temperature with precipitation rankings, we notice that the summer of 2012 actually ranked number 4 of all time, because not all hot summers are dry, and not all dry summers are hot, as we'll see later. So this was a truly remarkable year. Okay, here's a picture from the Drought Monitor. I've stripped off all the letters that they have on there. But as you notice, with the U.S. Drought Monitor, just before Hurricane Isaac, much of the Midwest was in this extreme drought category, which is the red, and exceptional is this brown category, which most of Missouri was in. And if you look at the United States as a whole, quite an area was covered by drought in some stage, whether it was drought stage 1 or 2 or 3. If you look at what's happened since August 28th, during the fall we didn't get much relief, unfortunately. And if you look at what's going on now, it's still very dry to our west. There's been some improvement to our east in Indiana and Illinois, but much of Missouri is still behind the 8 ball with precipitation. And I talked to my soil science colleagues, and they tell me that the ground reservoir of moisture is very low too. If you go down even a foot, we're lacking a lot of moisture. Okay, drought and flooding. When you get these kind of situations here in the United States, they're not short-term prospects. All right, they occur over a very long period of time. It takes a while to get into them, and it's going to take a while to get out of this. All right, we're not going to get out of it overnight. All right. If you look at drought conditions, you need to go back and look at, for the 2012 drought, you need to look back to last summer, the summer previous to that, summer 2011. All right. And even with the flood of 93, when you look at the conditions that led up to it, the previous 8 to 10 months had precipitation values that were much above normal over much of the plains region where the flooding was a big problem. So it's something that builds up. There is something called flash drought. My colleague, Dr. Gannan, likes to use that a lot. That's when you get a 6 to 8 week period where it's very dry, and you can dry out the top layers of moisture in the ground and have some problems, especially if the dryness comes at the wrong time. Flash drought was a particular problem in Russia in their 2010 drought. A drought over there happens differently from how it happens here, and I'll explain that later. Okay. We have to remember that with drought, we're dealing with two issues. All right, a lot of folks tend to look at just the precipitation aspect and track whether we're behind or ahead on precipitation. But you need to worry about the evaporation as well. And the drought of 2012 is a good case study for that. There were some dry months leading up to the drought of 2012. But the precipitation during the spring of 2012 was fairly close to normal. The problem was the spring temperatures were so far above normal and the relative humidity was so low that it took all that rain out of the soil. All right. And the spring of 2012 was a little windier than typical too. So you combine a little stronger winds with lower relative humidities, and you've got a recipe for drying out. All right. And that's how meteorological drought is looked at. It's looked at as the long-term conditions of precipitation minus evaporation. Okay. All right, there are different types of drought out there, and we classify them by what they stress. If you look at precipitation and evaporation, you talk about meteorological drought. You can have an agricultural drought, a drought that stresses plants and crops and things, or you can have what we call hydrologic drought that stresses the waterways and ponds and lakes and things like that. And obviously you can have all three together. 2011 was a great case because the summer of 2011 and even the spring to some extent were a little bit dry here, but we had extreme flooding in northwest Missouri and southeast Missouri because of the intense snow melt that happened in the upper part of the Midwest and came down the Missouri River. So even though things were relatively dry, the waterways here were pretty full. All right, let's take a look at the meteorology that goes with drought. What I'm looking at here is I'm looking at the atmospheric pressure or height about halfway up the atmosphere, 500 millibars, about 3 miles up, and can a lot of times be taken as a good representation of the jet stream. If you look at the average conditions from about 1 June to 31 August in 2012, what you notice here is a very amplified ridge over the United States. One thing that you can notice if you look at a lot of these maps is that in the northern hemisphere during the summer, all right, the flow is much weaker because we get rid of the temperature gradient. Typically what happens over the United States is you form some sort of ridge, and the variability in this from year to year is phenomenally low. All right. What makes a difference between drought years and non-drought years is the intensity of this ridge. How amplified is it? There'll be some years when this thing is moved over into the Midwest as opposed to the Rocky Mountains, but there's not a lot of variability in that either. All right, so what do we want to consider? If most summers take and look like this, with the exception of the amplification of the ridge, then we got to consider other factors. Now I'm going to show you a map that has the flow about 1 mile up, or about 850 millibars. All right. And I took this from a study that we did of dew points and the trends of dew point here in the Missouri region. Well, I don't know if you can see that, but I'll try my best to point out the relevant features. 1970, very dry year. Notice that you have a ridge there. 2001, it was a normal year. You still have a ridge. A little less amplified, but you still have a ridge. 76 was a dry year as well. What's the difference here? In 1970, in lower levels, your low-level flow was more or less out of the desert southwest. It was dry continental flow and fairly weak, making its way into Missouri. In a year where you have normal precipitation, this low-level jet feature is coming more from the south, but in a configuration where it's able to draw some of that moisture from the Gulf. Here's a year where it was very dry, but the jet stream the jet stream is a little bit shifted back to the west out of the continental dry areas. But in each case, again, the big difference was, where is our low-level moisture coming from? All right. Another thing that we consider in this year-to-year variability is, of course, the El Nino. El Nino is the 800-pound gorilla of year-to-year variability in the climate system. All right, it dominates variations on time scale of 2 to 10 years. Now, everybody knows that that's an impact for Missouri in the winter, and that ENSO's impact is more strongly felt in the winter, not so much in the summer. So what connection did we find between El Nino and our summertime weather? The connection we found was the transition, the direction of the transition. When you tend to go from El Nino to La Nina conditions, you tend to have a dry summer. When you tend to have neutral conditions and neutral conditions remain, you tend to have a very nice precipitation amount. When La Nina stays in force during the summertime and you have no transition, I should have probably put weak LN conditions, because that's what it was during the summer. But when La Nina remains during the summer, you tend to have dry conditions here. When you have very wet conditions, you're dealing with a transition toward a strong El Nino. So the connection that we've found is not El Nino itself, but the change in El Nino at time and the direction of that change. All right, El Nino, of course, refers to the warming of the sea surface temperatures in the eastern tropical Pacific down near Central America and Mexico. And this happens in the fall and reaches a peak around Christmas time. The Spanish, who came into contact with the indigenous peoples of South America, learned of this phenomenon, and in the late 1600s gave it the name El Nino, since it set in close to Christmas time. But El Nino wasn't known outside of that region, of course, until the 1920s. Okay. Well, the counterpart to El Nino is, of course, La Nina, and that represents periods of time when the oceanic temperatures in the tropics are cooler than normal. Now, climate is driven in the atmosphere somewhat internally, but is largely driven by external features, such as the heating or the heat distribution at the surface of the Earth. If I change that, then I change the heat and mass distribution in the atmosphere, and I consequently change the jet stream. And that's how ENSO impacts our weather. All right, so when Chris was talking about the difficulty of models to get a handle on our summer precip because of the location of because of the difficulty in getting a handle on the location of the jet stream. That's what that's referring to. Okay? That's how El Nino impacts our weather. All right. Like I said, El Nino represents changing the heat distribution in the ocean. Usually, the waters of the West Pacific are quite a bit warmer than they are in the East Pacific. You get a lot of convection and rain in that part of the world. And then when El Nino sets in, warm water migrates but also develops in place, and the convection comes with it. And when you bring that atmospheric convection over, that atmospheric convection again is helping to redistribute heat and mass, and consequently the mid-latitude jet. What's going on now? Well, here's the sea surface temperatures, again, very warm in the western Pacific. There's pockets of cool and warm temperatures here in the eastern Pacific, and that shows up in the anomaly map as well. Right now we're in ENSO neutral conditions, as Chris was saying earlier. Okay. The forecasts, if I use both dynamic and statistical models, again, this is a blend of both types of models, dynamic and statistical. Here we are, November, December, January time period, here we are here, and this is what they project for the upcoming year. They project things to remain in the neutral area. So what does that mean? As Chris pointed out, it's hopeful. All right, how did we establish that it was the transition of ENSO? We had a study a few years ago where we looked at the summertime regime and how it becomes established here. Generally what happens is that significant rains will fall in Missouri on an average of about 7 days. But if you look at spring and summer separately, all right, we get significant spring rains, average of about 7 days. This becomes 12 days after the onset of the summer pattern. It's this that we saw transitions in. If you're going toward a future El Nino situation, all right, the summer frequency of rains are about 10 days. All right, they come more regularly, and they're better rains. Less amount of it, less heavy, and more widespread. Better for agriculture. Sometimes this happens in the extreme, as in summer 93, but summer 2004 was a wonderful example of this. The rains came regularly and the crops were great. When you transition toward La Nina, or La Nina remains in place over the summer, that's when we get our historic droughts. 83, 88. 99, 2005 weren't so bad. 2012, La Nina weakened, but it was slow to give ground. 1950s, 3 straight years of La Nina conditions. All right. There isn't a huge difference in the actual amount of precipitation, but it's just how it's distributed. All right, in a La Nina year, that precipitation comes less frequently and tends to be heavier. And of course, we know that in agriculture, we want the rains to be more frequent and not as heavy. We don't want the precipitation running off. All right, so the results of Ratley did this on a 30-year period. We extended it from 2000 to 2012, adding another 10 years to that. I'd love to go back to 1900 and see if these same correlations are showing up. But you know what? We looked at 40 years worth of data with our Russian colleagues, and it's turning out that the transition is also important in Western Russia as well. And in fact, for Moscow and that region, it's the same type of transition. You go toward La Nina, they're going to get a higher frequency of drought. So it works elsewhere. And of course, we presented this at a conference just recently. All right, I'm going to wrap that up. I'm not going to talk about climate and climate change because I only got a half hour, and I believe I'm almost exceeded that. So Chris did a fine job in talking about how climate change may affect the frequency of drought. We know that Missouri, and in particular our region, with precipitation, it's feast or famine. So, and in order to get people to come see me later, let's go forward. Oh, I forgot to give a good shout out to the Treering Lab because I've used a lot of their results, Mike Stambaugh and Rich Guyette. What's in store for 2013? Come and see. Any questions?
Thank you very much, Tony. I think we can still take a couple of questions. Well, perhaps you can tell us what is in store for 2013.
Well, let me get through the first few slides of that, because in the first few slides of that, we pat ourselves on the back for the last two long-range forecasts and how well we did. So we're forecasting right along the lines of the Climate Prediction Center. Probably the temperatures will be slightly above normal, nothing to write home about, but as Chris says, the precipitation, CPC always punts on the summer precipitation. And that's because so much of it in our region is convectively driven. We're going to stick our neck out and say it's going to be very close to normal, as Chris was saying. I was thinking that it may be slightly on the dry side of normal, but close to normal. So. Any other questions?
Well,
all right.
If not, Tony, thank you very much.